Hello everyone, myself Deepa Singh, working as assistant professor in Gyan Vihar School of Pharmacy, SGVU, Jaipur. Today we discuss about one compartmental open model IV bolus compartment. So these one compartmental open model we already covered in previous lecture. In this we already covered IV infusion and extravascular compartment modeling. So today we discuss about IV bolus. IV bolus is one of the compartmental type of one compartmental open model. This is containing three models. IV bolus, IV infusion, and extravascular. Extravascular and IV infusion we already covered. And today we discuss IV bolus compartmental model of one compartmental open model. It is a topic of biopharmaceutics and pharmacokinetics subject, 6th semester subject. So before starting this topic, you should know about some learning objects. So in this learning objects, you should know about introduction of the one compartmental open model. Means you should know about because we already covered these, the description of one compartmental model and what is compartmental modeling and difference between these compartmental modeling. So you should know about what is one compartmental model, assumption of one compartmental model, which are the assumption and how you perform the study of one compartmental model, including some assumptions. So you should also know about some assumptions. And the next is one compartmental IV model. For IV bolus administration, how you calculate the value after administration of drug by IV bolus administration. So you should also know about IV bolus administration with their derivatives and their calculation part, and how you perform these IV bolus administration. So in this assumption, the one compartmental open model is a simple model owing to its simplicity and based on the following assumption. These are the assumption of one compartmental open model. In this, the body is considered as a single, kinetically homogeneous unit, has no barrier to the movement of the drug. Name itself indicates that it is a one compartmental model, means a complete procedure is takes place by a single part, or you can say that body considered a single kinetic homogeneous unit because only one compartment is involved in this, and no barrier to the movement of the drug, means no any other barrier or any other compartment in this one compartmental model. It is have only one single compartment homogeneous unit. Next is final distribution, equilibrium between the drug in plasma and other body fluid, that is mixing is attained. And this final distribution is also achieved at equilibrium position or equilibrium condition with other body fluid and attended by intertaneously and maintained all times. And the model does apply only those drugs that distribute rapidly throughout the body. Means these one compartmental open model IV bolus, not only IV bolus but all the one compartmental open model have some assumption, and it is limited for only those drugs who have rapidly distributed out or uniformly distributed out in your body without any problem. So this is also drug limited condition. And drug move dynamically in absorption out elimination of the compartment. Thus, it is a process in which drug get absorbed and eliminated out through body. And the elimination process is a simple process in one compartment. After absorption, remaining drug get excreted out or eliminated out in your body. Next is elimination in first order mono-exponential process with first order rate constant. Means it follow mainly first order kinetics or first order rate reaction mono-exponential process. And in this elimination is mainly we see that first order reaction. So these are the assumption. Out of this, some another assumption is like rate of input, that is absorption. Input is nothing but your absorption of the drug is more than rate of output, that is elimination. Is in this one compartmental open model, we always see that rate of absorption is always less compared to elimination. More drug eliminated out or rate output is more observed in one compartmental model. Next is the anatomical reference compartmental. This plasma and concentration of the drug plasma is represented by drug concentration in the body tissue. This main anatomical reference or main part is your plasma and compartmental in plasma concentration drug, and this represents the concentration of a drug in all your body and how much drug present in all your body. Any change in plasma concentration reflects a proportional change in drug concentration throughout the body. Means any changes is takes place in your plasma concentration, then it directly affects your compartmental body or concentration present in your body or drug concentration present throughout your body. So these changes is also affect your plasma drug. Plasma drug concentration also affect your concentration of a drug present in your body or in your plasma. And however, the model does not assume that the drug concentration in plasma is equal to other body tissue. Means this one is also one assumption in this model. We does not assume that the drug concentration in plasma is equal to that in any other body tissue. So these are the assumption of one compartmental open model. In diagrammatic representation, there's one, we can say that body, and this drug get in means absorption is takes place, and drug get out. So this is the elimination rate. And in this, there's body parts where the major this process takes place: lungs, liver, kidney, heart, fat, muscles, as all included in one compartment. And it is a simple body where the key constant or elimination rate takes place. When we plot the graph of this compartmental model, we plot the time versus concentration. So in time versus concentration, we plot that how much drug is eliminated out or excreted out through that particular site. So this is a representation way of how much drug is that particular site. This is showing muscle, and this is showing plasma, and this one is for kidney. And in time versus log concentration, we plot time taken in hour. This is how much time is required for particular concentration. Next, the term open indicate that the input availability and output elimination are in unidirectional, and some drug can eliminate it from the body. Now, one compartment is such that there's no direction or it is only one direction, means it indicates that when input and output are comes in a unidirectional in the same direction and eliminated from your body. And in one compartmental open model is generally used in describe the plasma level following administration of a single dose of the drug. So mainly we can say that one compartmental open model uniformly flow in unidirectional or in a single direction. Absorption after this elimination takes place. So in this elimination, we see that diagram. This one is drug, and it goes in your body. And this one is output, that is absorption is takes place, and body distributed in throughout your complete body parts, blood as well as other tissue. Then it may be excreted out or elimination is takes place. This is the output, and in output may be metabolism and excretion is takes place, because elimination is further divided into two categories: metabolism and excretion. So after this blood and other tissue transfer, it get eliminated out. In this elimination, it is further divided into two parts: metabolism and excretion. So this is the procedure how the absorption and elimination takes place in one compartment in unidirectional way. Next is depending on the rate of input, following one compartment open model can be classified. And this is the overall model for one compartmental open model. According to this rate input and output, we are decide this. These are the different compartment modeling for one compartment. In this one compartmental open model IV bolus administration that we today discussed, one compartmental open model continuous IV infusion that we already covered in previous lecture. Next is one compartmental open model extravascular administration or zero order absorption. This one is also we have covered. Next is one compartmental open model extravascular administration, first order absorption. So these second, third, and fourth models we already covered in previous lecture. Today we discuss about IV bolus administration, one compartmental open model. These all four compartment are comes in one compartmental open model study. So in one compartmental open model IV bolus administration, in this IV bolus administration, when drug distributed rapidly in the body in the form of rapid intravenous injection, it about 1 to 3 minutes to complete circulation, and therefore rate of absorption is neglected in calculation. Model can be replicated as means this is mainly calculation for when the drug is given in intravenous injection or by the IV route, and when the administration takes place. So the complete drug is within the 1 to 3 minutes that completed in circulation, comes in circulation. And after this rate of absorption is neglected, because this is a very rapid process in this calculation part, and the model can be replicated is like this. Blood and body other tissue means your drug is present in your body, blood as well as any other body tissue, and then eliminated out. This one is rate output where the elimination takes place. This one is a general equation representing the IV bolus compartment modeling. In the general expression, rate of drug present to the body. This is the rate, how much drug is present in the body or representing the drug present in your body. So in this dx by dt is equals to rate in availability, means absorption minus rate out, that is. We just minus absorption amount with elimination amount. So this represents the complete expression of rate of drug present in your body. Since rate in absorption is absent, equation become means these absorption we are just neglecting. We already discussed in previous slide because it takes place within 1 to 3 minutes when we neglect this rate absorption. So this equation is modified form, that is minus rate output or rate of elimination in minus. Next is rate on out and elimination of follow first order kinetics. Then means these rate elimination or rate out is suppose follow first order kinetics. Then this modified equation is like this. Dx by dt is equals to Kex, where the K is the first order elimination rate constant and X is the amount of a drug in the body meaning to be eliminated, and the negative sign indicate the drug being lost from the body. Because drug is not present in your body, it get eliminated out or excreted out. That's why we're putting minus sign. And so minus sign indicate the loss of drug from your body, and X is the amount of drug in any time remaining to eliminate it, and first order elimination rate constant is Ke. So this is equation for the drug present in your body in the IV bolus administration after modification. Next is estimation of pharmacokinetic parameter. IV bolus administration means how you estimate these pharmacokinetic parameters. It is administered by IV bolus route. So in this for a drug that follow one compartmental kinetic administration as rapid IV injection, the decline in plasma drug concentration is only due to elimination of a drug from the body, not due to distribution. The phase being called as elimination phase. Means in this, we are not considering that absorption phase because your drug is completely distributed out, and this is a fast procedure, and main procedure is elimination from your body. So this one compartmental kinetics and administration by IV injection is decline in plasma drug concentration is only due to elimination of a drug from your body and not due to distribution. And in this phase, being called as elimination phase, and elimination phase can be characterized by 4 parameters. Means this declining phase and this elimination phase, the removing of a drug in your body or a decline phase is known as elimination phase. And elimination phase consists of 4 parameters. These are the 4 parameters which represent the elimination phase. So in this, first is elimination rate constant. Second is apparent volume of distribution. Third one is elimination half-life, and fourth one is clearance. So these are the 4 pharmacokinetic parameters for estimation of IV bolus administration or IV bolus administration of the drug. So these estimation parameters now we discuss one by one. This is mainly for elimination phase or determining of IV bolus administration and estimation of pharmacokinetic parameters. So then elimination rate constant, first estimation parameter of pharmacokinetic or elimination phase. So this elimination rate constant is represented by Ke. And elimination rate constant represents the friction of a drug removed per unit time. Means how much drug removed at a particular time period or at per unit time. Then suppose in 1 hour how much drug is removed, or after 1 hour how much drug get removed. So this elimination rate constant is represented by fraction of a drug or how much drug is removed per unit time from your body. Next, K has a unit of reciprocal time. So this K is also represented constant time or reciprocal time in minutes, maybe hours or day, depending on the type of drug or elimination rate of the drug. So this reciprocal time represent how much drug is at particular time, constant amount, with a time, hour or day unit. With first unit elimination, the rate of elimination is directly proportional to serum drug concentration. Means this first order elimination or rate elimination directly proportional to serum drug concentration or how much drug serum present in your body. So this elimination rate constant is also represent serum drug concentration of your body. Next, in continuation elimination rate constant, equation is this. So the equation that represents the rate constant or elimination rate constant is dx by dt is equals to Kex. Now integrating this equation is for only the elimination rate constant, representing the how much drug is eliminated out from your body. When you integrate this equation, then it converted into this equation and give this equation. In x is equals to in x0 minus Ket. This is integrated equation of previous one or elimination rate constant integrated equation, where x0 is the amount of a drug at time t. Means x0 is the amount of a drug at particular time period. Means suppose in 1 hour or 2 hour at particular minutes time, how much drug is present in your body or amount of drug at particular time, and t is the 0. Above equation can also written the following mono exponential format as when modify this integrated equation or writing down in mono exponential form, because this one is one compartmental model. So after modifying this integrated equation in mono exponential form, we solve this equation. X is equals to x0 e minus k e t e. So this is a more exponential form of elimination rate constant equation. Next, above equation we can write in a log form, base 10 form s, means these more exponential log x is equals to log x0 minus ket divided by 2.303. So this equation is also elimination rate constant form, rate constant for this log form equation. Since it is difficult to determine that the amount of drug in the body x, means how much drug present in your body is representing the x. And advantages is taken that the fact that constant relationship is present in your body, and C is the concentration of a drug or how much drug present in plasma concentration. So when we simplify this equation or changing some parameters according to condition or according to how much drug present in your body. So when we change this equation, we see that X is equals to VD into C. So this is volume of distribution, VD, and C is the concentration in your plasma drug concentration. X is the total amount of drug that is distributed out to your body. So this is a simplified equation where we did a proportionally constant, popularly known as apparent volume of distribution and volume of distribution both are same. So this is the equation for the elimination rate constant. Next is a graph. In this, we are plotting a time versus concentration graph or drug concentration. So when we plot one graph, there's a decline condition is obtained. And in this, concentration is mainly taken by KET. And next, this one is time versus log C. So this graph gives a straight line in declining condition. And in this graph, we receive this equation in a logarithm form because this is just a changing form of log and converting when we log or log apply. So this equation or graph is often is like this. So in this log, x is equals to log x0 minus KET divided by 2.303. So this is a log equation of this one compartmental open model. Now apparent volume of distribution, suppose this is to body condition, or we are just saying that this two bigger we are considering one body. In this 10 liter, that is concentration is to 10 mg per liter, 10 ml is total concentration present in the fluid, and in this there's 10 mg concentration drug in per liter is present. And when we say that in this total amount is 100 mg of your drug, and in this is also same condition is instead of 10 liter, we are considering that there's a 100 ml. So this is just too much extra compared to this one, and concentration is 1 mg per liter because here the fluid concentration is also high. That's why drug is, concentration is 1 mg per liter, and this is 10 mg per liter. Apparent volume of distribution may be defined as the hypothetical volume of a body fluid into the drug is distributed. Means apparent volume of distribution is nothing but one hypothetical volume or hypothetical volume which is present in your body fluid or in your body. This drug is get distributed out uniformly throughout your body. And there's the amount of a drug which is present in body fluid or in your body. And when we administer the drug, it distributed out in your body completely in uniform way. So this is the volume of distribution. Next is apparent volume of distribution. So volume of distribution is the volume of distribution. Represent the volume that must be considered in estimating the amount of drug in your body. Means how much drug is distributed out or how much volume must be present in estimating amount of drug in your body or how much drug present in your body from the concentration of a drug found in sampling compartment. Means volume of distribution is nothing but the volume which is present or we are considering the amount of a drug in your body, estimating the amount of drug in your body from the concentration of a drug for that particular sampling compartment or that compartment that we are considering for a study. So this is nothing but the concentration of a drug which is present in your compartmental modeling. and in general equilibriums rapidly in the body. And plasma or any other biological compartment is sampled. And this is also one of the equilibrium condition, or we can say that equal condition in your body, where the plasma drug and biological compartment is sampled and analyzed by drug contain, and the result is usually reported in unit concentration instead of amount. In this, we are considering or withdrawing the sample from your body or taking the sample of your body fluid. In this, how much drug is present analyzed, how much drug present in your plasma concentration or in your plasma. So in this, drug equilibrium rapidly in your body when plasma or any other biological compartment is sampled. Means maybe we can take plasma as well as any other body parts for sampling or for analyzing the amount of the drug. In this, we can take maybe plasma or any other biological compartment in sampling. And after taking this sample, we can analyze the sample for drug content, how much drug is present, and you should report a unit concentration instead of amount. We are representing this concentration in unit instead of amount drug present in your body. So after collecting the sample from plasma or any other body parts, we are just analyzing these concentration with the help of how much drug content present and reported in the unit concentration instead of amount. And each individual tissue in the body may contain different concentration. Means we can say that throughout your body there's no same concentration. The concentration of a drug may be vary. It is obvious because throughout your body your drug is not uniformly accumulate or maybe it will flow out. So there may be variation between your drug present in your body and according to various tissue. So each and every individual tissue in the body contain different concentration of a drug due to difference in drug affinity for that tissue, and therefore the amount of drug in your given location can be related to its concentration by proportional constant that reflect the volume of fluid in drug dissolved in. Means we don't calculate how much drug present at particular tissue because every tissue have a different affinity or different affinity for particular drug. So these affinity, according to these affinity or according to particular tissue, we are calculating how much drug present in your body or particular tissue according to the affinity, and this is mainly calculated by some other proportion constant or a particular amount of drug in particular tissue, and we are just saying that this amount is present and total body fluid is this amount. So according to this, we can calculate the volume fluid in dissolved condition in your body. This is the real volume of distribution. So total body water is 42 liter. Means in every person or healthy person, total body condition or fluid containing is almost 42 liter. Every person contains 42 liter water. So according to this 42 liter, this is the distribution of fluid content or water content of particular human being. In this first is plasma. The plasma consists of only 4 liter water out of 42 liter. In plasma, there is 4 liter is water and remaining is a fluid. So out of 42, 4 liter is in plasma. Next is interstitial fluid. So an interstitial fluid is almost 10 liter. Means out of 42 liter, total is interstitial fluid is 10 liter. So including plasma and interstitial fluid, only 14 liter water is present out of 42, and remaining 28 liter present in intracellular fluid. Means largest amount or large volume of water present in your intracellular fluid or intracellular parts. So this is the distribution of 42 liter water. Means healthy person or healthy human being contain 42 liter water, and this is largely out of this 42 liters largely present in intracellular fluid, that is 28 liter almost out of 42 liters, and remaining 10 liters present by interstitial fluid, and in plasma is only 4 liter water is present out of 42. This is the volume of distribution according to body fluid present in your body, water present in your body. Next, in this apparent volume of distribution, drug which binds selectively to plasma protein, warfarin, have an apparent volume of distribution. Means according to the affinity or according to selectivity to particular site drug can bind, because every drug don't have a same affinity to that particular site or particular tissue. They may depend on the condition or the property, how much affinity to that particular tissue of that particular drug. So this binding is depending on the selectivity to plasma protein, and warfarin have an apparent volume of distribution. Means this warfarin is also show that some apparent volume of distribution for a smaller than real volume of distribution. And Drug which binds selectively to extravascular tissue, that is chloroquine, has an apparent volume of distribution larger than the real volume of distribution. And we see the binding property in extravascular tissue. So in this one drug is example like chloroquine type drug have an apparent volume of distribution larger than the real volume of distribution. Means real volume of distribution is less compared to apparent volume of distribution is more observed in this condition. And the volume of distribution such drug is always greater than 42 liter, that is total body water. So this is very high in this type of the drug or in extravascular tissue because water containing is also present high in the tissue fluid or extracellular fluid. So this is and volume. After this, lipid solubility of how the apparent volume of distribution is responsible or distributed out to your body. So these are the some factor or responsibility. According to this, what apparent volume of distribution get distributed out to your body. So in this first is lipid solubility of a drug, means how much drug is lipid soluble, because lipid soluble drugs are more appropriate and good in nature for showing maximum effect or majority of effect. So this apparent of volume distribution is also depend on lipid solubility of a drug, how much drug have easily solubilized in oil soluble or affinity of a particular drug in lipidic in nature or oily in nature. Next is degree of plasma protein binding. After that particular lipid solubility, we can also check that plasma protein binding or how much drug is easily bind with plasma, because majority of drug can easily bind with plasma protein. If more drug is easily bind with plasma protein, so that in this condition more drug can show effect and less is eliminated out. So this apparent volume of distribution is first depend on lipid solubility of a drug. So more lipid soluble drugs show more distribution compared to water soluble drug. Second is degree of plasma protein. In this, more plasma protein drug binding is required for showing more effect. Next is affinity for different tissue protein, means according to different tissue or a different site, the affinity of a drug may vary, or a particular tissue it can bind more or it can bind less in particular different tissue. So the affinity is also important parameter. This affinity is depending on the drug nature or type of drug to that particular tissue, how much drug is bind to that particular tissue or affinity to particular tissue. Next is fat. In this land body mass, suppose in this fatty person there's a less distribution of drug takes place, or maybe more distribution of fatty material or lipid soluble drug is observed due to more fat present or more mass present in that particular body. So out of this factors, fat is also one of the important factor which is responsible for also distribution of a drug, how much drug is distributed out. In a body fat condition, we already see that if person is fatty or having a more mass fat, so in this condition, lipid soluble drug that easily distributed out and compared to water soluble drug, and some drug maybe have show some affinity problem like water soluble drug don't get easily distributed out in fat material. Next is disease like in this congestive heart failure. If person suffering from any other disease or multiple disease, in this condition volume of distribution or this absorption procedure may be vary. This volume of distribution is not similar. It may be vary if person have a certain severe disease like congestive heart failure and uremia, cirrhosis. So this in this is condition or these type of a disease condition is also affected volume of distribution. It also uniform distribution of the drug. Next is in order to determine the apparent volume of distribution of the drug, it is necessary to have a plasma and serum concentration versus time data. We are just saying that plasma and serum concentration data we are plotting, and with the help of this plasma and serum concentration data versus time, we are decide that how much apparent volume of distribution is present in your body according to mathematical equation. This is the equation for apparent volume of distribution according to drug or maybe according to ratio of plasma drug or serum drug present in your body versus particular time. So in this VD is volume of distribution is equals to dose versus initial concentration. Then particular dose or initial starting concentration. And when we simplify this equation in mathematical equation, so this is X0 divided by C0. So this is a mathematical representation of apparent volume of distribution for one compartmental model or for IV bolus. This is the extent and distribution of VD in 70 kg normal man. This is an example how the volume of distribution takes place in normal man and whose weight is 70 kg. So this flow chart or this diagram or this table show that particular volume of distribution to that particular person in 70 kg weight. And in this, first is volume of distribution, second is person body weight, and second is of distribution. Next is example is volume of distribution in liter. Means a drug at particular volume of liter. And in this volume of distribution, first is 5 and low, body weight is 7, and extent of distribution only in plasma. An example in volume of distribution is warfarin, 7 liter, and volume of distribution in liter is 50 to 20, that is medium, and body weight is 7 to 28, and extent of distribution is in extracellular fluid, that is ibuprofen 10. In 10 liter is your volume. Next is this for high condition, volume of distribution is 20 to 40 for high, and body weight is 28 to 56, and extent of distribution in total body fluid. Next example in this theophylline, that is volume of distribution is 50 liter. And after this, there is a very high concentration, that is more than 40 liter. And in more than 40 liter, person body weight is 56 or more than 56. And extent of distribution is in the tissue bound peripheral tissue. An example of a drug is like ranitidine. Volume in this ranitidine is 500 liter, and in chloroquine we can say that liter is 15,000 for your chloroquine. So this is the volume of distribution for normal man with 70 kg weight. Next is significance of volume of distribution. So in significance, it simply indicate how widely drug is distributed in the tissue compartment to the plasma, means how much drug is distributed out that particular tissue or that particular plasma drug concentration. For example, VD of paracetamol is 0.5 liter per kg body weight. So it means that 0.950 liter of a tissue is expected to contain the same concentration of paracetamol as that contain the blood on the basis of average kg body weight. So this is the amount that indicate the significance of volume of distribution in your body. So this simply indicate that how much drug is present in that particular tissue or that compartment. In this volume of distribution, we are considering that 0.950 liter in that particular kg in weight. And these 9.50 liter in this particular tissue is expected to contain the same concentration of paracetamol as that contain the blood basis of average kg body weight. And next is, it does not mean that remaining tissue contains zero drug concentration. It is conceptually assumed and pressed in manner. Means you don't say that this amount is fixed amount and remaining tissue don't have any of the containing drug. So also have some concentration in any other tissue, remaining tissue. It don't have a zero condition or zero value. And continuation significance, higher volume of distribution or more extensive is volume of distribution in the tissue. Means more the volume of distribution, it's to more extensive distribution in the tissue or that particular extensive tissue. Next is, if the plasma drug concentration is low, it can be interpreted that volume of distribution higher for given dose. Means plasma drug concentration suppose is low, then this is referred as volume of distribution is higher when dose of drug is given is high. And that volume of distribution is 100% of a body, then it may be consumed that the drug concentration in certain tissue compartment. Means in some condition we say that this is the 100% body drug distribution or volume of distribution to that particular body. So in this condition, we are assuming that concentration of the drug to that particular tissue compartment. And next is, if the drug is restricted to the vascular space and can freely penetrate erythrocytes, the drug has a volume and distribution of a 6 liter. So this is the particular site or vascular space where the drug is freely penetrate or easily administered in erythrocytes. In this volume of distribution is 6 liter. And if the drug cannot permeate through RBC, the available space reduced up to 3 liter. Means just to half. It reduces 6 to 3 when it do not penetrate to RBC or erythrocytes. Next is elimination half-life. So this elimination half-life is sometimes called as biological half-life of the drug. Means another name of this elimination half-life is also known as biological half-life of the drug. In this, we can say that how much drug is show the half of the effect, or we are just calculating or checking the effect of drug in half of the condition or half of the concentration. So this is also another name is biological half-life of the drug. So in this, elimination half-life is defined as a time, and H is the minute of the day. In this, at a mass or amount unchanged drug become a half or 50% of initial mass of the drug. So this is the formula that represents the time, and in which mass or amount of drug is unchanged and become a half, that is 50% to initial mass of that drug. That is T half is equal to 0.693. divided by Ke. So this represents the elimination half-life equation. Next is increased physiological understanding of pharmacokinetic, that half-life is parameter that depend on primary parameter clearance and apparent volume of distribution. According to this equation, we are just simplify this equation, which represents the increased physiological condition of pharmacokinetic. So half of the parameter depend on its primary parameter. So according to this equation, we can say clearance, apparent volume of distribution, and we keep T half is equals to 0.693 volume of distribution divided by total clearance, that is clearance T, CLT. Next is a clearance. So in this, clearance is the measure of the removal of the drug. Clearance name indicates itself, see that amount of a drug that can clear or remove from your body. So this clearance is the measure of removal of a drug from your body, means how much drug is clear or removed or eliminated out from your body. So in this, plasma drug concentration are affected by a rate at which drug is administered. Means these plasma drug concentration is also depend on rate at which how much drug administered, administration rate, and volume in which distributed, and clearance, how much drug is volume distributed out and clearance out. And the clearance and the volume of distribution remain its half-life. So in this, we are calculating volume of distribution and clearance rate in half-life. Half of the drug is cleared out or distributed out in the body at particular time. And it is the most important parameter in clinical drug application, and it is useful for evaluation of mechanism why drug is eliminated by the whole organism or particular organism. Hence, these parameter is very important in clinical purpose, or when we are required the readings for clinical readings or clinical drug application. And this is useful for evaluating the mechanism. And this is also show that some mechanism by drug is eliminated by a whole organism or by a particular organ. And so this is also for depending on whole organism, particular organism of the drug. Next is clearance, that is expressed as a volume versus time, and describe the removal of a drug from your volume of plasma in given drug time. So this clearance is expressed in volume versus time, and removal of drug from body plasma in unit per drug loss from your body. And the clearance rows indicate the amount of drug being removed. It indicates the volume of plasma. Means it is also indicated how amount of drug or how much drug present in particular removal amount. And it indicates the volume of plasma in blood on which drug is completely removed or cleared in a given period of a time. Next is figure in the following two slides representing the weight of the drug clearance. In this first condition, the first figure the amount of drug, that is number of dots, decrease but fills the same volume, resulting in lower concentration. And second is another way of viewing the same decrease would be calculate volume, that would be drug free if concentration were held at represented in the second figure. So this is a two figure. This first is initial concentration, there's a more dotted drug is present, and second is resulting concentration is less drug is or scattered condition is present. This is elimination over time. In this amount of drug, the number of dots decrease, the field same volume resulting in lower concentration, and this is a condition. The dotted amount of drug is well decreased due to the lower concentration, or when decreases field for the same concentration of the volume. In second condition or second diagram, this is a dotted line, which is also more initial concentration, and resulting concentration it gets low due to the elimination over a time. So this is elimination over time, reduces the concentration or dotted concentration of your drug. In this volume from which drug is removed over a time. In this clearance continuation, the most general definition of clearance is that proportionality constant describe the relationship between the substance of elimination, means how much drug is eliminated out, and the relationship between substance rate of elimination, amount of per unit time, is how much drug is present at particular time rate per unit time. At time, the corresponding concentration is appropriate for at that particular time. And the clearance can also define as hypothetical volume of the blood, means the clearance is another name, is like hypothetical volume, or we can say that is a hypothetical volume in the blood or plasma and serum or other biological fluid which can be drug is totally irreversible removed per unit time. Means it is an irreversible process. In this irreversible process, the drug is removed per unit time in a particular time rate. This is a clearance estimation in one compartmental kinetics. So clearance is equals to Ka into Vd, means constant is equals to volume of distribution. Clearance rate is equals to constant amount into volume of distribution. So this is a clearance estimation. Clearance is equals to constant K into volume of distribution, that is VD. Next is clearance can be declared by body by different pathway organ, including hepatic biotransformation, renal binary excretion. So these are the excretion sites or tissue. The total body clearance is sum of the clearance of various mechanisms. In this equation is equals to total clearance is equals to clearance in R, clearance in hepatic, and plus other. Means maybe renal clearance, maybe hepatic clearance, or any other tissue. So total clearance is represented by sum of all the clearance. And in this clearance, CL, CR, CRH is the total renal and hepatic clearance. Next is elimination rate constant. So this elimination rate constant is nothing but the time that is calculated by a particular time or estimated rate for your drug. So in this we calculate the elimination rate constant of a drug, then K into K. Clearance into C, that is concentration, into T, where the XT is the amount of a drug in your body at particular time period. Means total amount of a drug or concentration of a total of the drug. CT is the concentration of the drug at particular time. This is the total concentration and this is the normal concentration of your drug. So this is the amount of drug and this is the concentration of a drug at particular time T. After completing this lecture, one compartmental open model. These learning outcome is depending on this lecture. So in this introduction of one compartmental open model, what is one compartmental model and how it takes place, and different assumptions that we already covered, which assumption is major or show the problem during we are using this IV bolus compartmental model. So assumption of one compartmental open model. Next is one compartmental open model for how it takes place after IV bolus administration, including clearance, volume of distribution, elimination of the drug. These all parameters of volume of distribution we already covered. So you should know about these parameters, including this equation and why you writing this equation and which condition is affect for the particular drug. So these are the learning outcome. After this learning outcome, these are the reference part. All references are good. You can use any one of reference or in a combination for this topic. In this first is Remington, the Science and Practice of Pharmacy, 24th edition. Page number is 672 to 685. Next is Brahmankar, textbook of biopharmaceutics and pharmacokinetics, 3rd edition, page number 15 to 48. Next is CBS Subramaniam, textbook of physical pharmaceutics, 2nd edition, Vallabhakashi. Next is Zambarkar, S.S. Green, BJ, Basic Pharmacokinetics, London Pharmaceutics Press, 2009. Next is Sanjul L. V. Pong S. UAPC, Applied in Biopharmaceutics and Pharmacokinetics, Amsterdam Hill, 2007. So these are the references. After this, these are the questions which is related to this topic. After completing this lecture, you can easily answer this question. These questions are very simple question. In this first question, what does the word open means in one compartmental open model? In option A is the drug easily enter. B is drug is readily mixed with blood. C is unidirectional input and output. D is easy to absorption. In second question, how much time does intravenous administration takes to complete the complete cycle? In this, A is 5 to 8 minutes. B is 7 to 10 minutes. C is 1 to 3 minutes. D is 1 minute. These both questions we already discussed in this lecture. And the next in third question, in the equation concentration C is equal to log C0 minus KET divided by 2.303. What does CO stand for? Is a plasma drug concentration after 30 minutes of IV injection. Is a plasma drug concentration after 15 minutes of IV injection. And C is a plasma drug concentration after 30 minutes of IV injection. And D, plasma drug concentration immediately after IV injection. Next in fourth question, what is mean by elimination half-life? And this is a time taken for half of the amount to get completely eliminated from your organ. B is the time taken half of the amount of drug get completely eliminated from your body, blood. And C is the time taken half of the amount of drug get completely eliminated from only plasma. And D is the time taken for half of the amount to get completely eliminated from your body as well as your plasma. So these third and fourth question already we discussed and covered in this paper. So you can answer this question. And fifth question, which is the equation to find out the apparent volume of distribution, is the amount of drug in a body in plasma of drug concentration. Is a plasma drug concentration and amount of drug in your body. So is the one divided by plasma drug concentration. This is the one divided by amount of drug in your body. So this is the fifth question. And this next sixth question, IV bolus dosage is 500 mg and plasma drug concentration is 0.8 mg per ml. What would be volume of distribution? In this A 625, 625 ml, B is 0.0016 mg per liter. So these are the 5 and 6 questions that you can also answer. And seventh question, to have a plasma distribution value of 900 ml and plasma drug concentration 1.2 mg per ml, what should the amount of drug should be given to the patient? A is the 1080 ml, B is 1080 gram, C is 1080 mg, D is 1 gram by ml. And eighth question, what is the equation? Find out the hepatic clearance. In this is the plasma drug concentration and the rate of elimination by kidney, or ratio of rate of elimination by kidney and plasma drug concentration. This is the 1 divided by rate of elimination by kidney, and D is the 1 divided plasma drug concentration. So in next ninth question, mathematical concept which describe the space in the body which drug appear occupy is the order reaction, B is compartmental, C is distribution, D is elimination. In 10th question, or in last one, the manner in which drug is taken. A is the dosage regimen, B is dosage volume, C is the dosage loading, D is dosage regimen. So these 10 questions are very simple, which is related to today's topic or this lecture. If you completely understand this topic, then you can answer this question. So this question is related to this topic. So thank you so much for watching and listening to this video. Thank you, everyone.